Hello everyone. In this video, we are going to finally talk about the stiff differential equations as well as A and L stability. So what is a stiff equation? Although there is not really a very clear definition of stiff equation, but we can say it is an ODE for which some numerical algorithms are numerically unstable. Why? Because if you look at it, there are some terms in it that can lead to rapid variations in the solution unless some very small step size are taken. So basically it means that if you use any method like Runge-Kutta or anything else on a stiff ODE like this one, y prime equals y squared minus y cubed, where y at 0 equals some small number delta and t goes between 0 to 2 over delta. This is the equation for propagation of flame, where here y is the radius of the ball. If you want to solve this using ODE 45 that uses Runge-Kutta, then there are some regions in it, specifically for this one, this region, where it is kind of trying to go to a steady state value. In this region, although it looks very kind of flat, but if you zoom into it, and I'm going to show you, there are lots of oscillations here. And if that is because the numerical solver wants to basically solve that, but remember from the previous step that the step size has to be at least so much, or at max so much, such that the error falls below some threshold, right? And so, because the error is too big here, the step size is reduced, and then the error goes below threshold. And as soon as the step size wants to increase again, the error goes above the threshold. And you see a lot of these overshoot, undershoot, and a lot of these oscillations. So the only way that ODE 45 can work is when basically you have a lot of small steps, and your step size here is taken to very small numbers. That's why you see for this simulation time, this ODE 45 is taking about 12,000 steps, which is quite a bit. But if you use an algorithm, an ODE solver that is designed to handle stiff ODEs, something like ODE 23S, you see it can handle this entire time range with only 100 steps. Okay, so some solvers would not capture the dynamics of the system and get a solution with reasonable error unless you take a ton of small steps. Okay, but some other ones that are designed to handle it, they can easily do it with a lot smaller steps. That's why this kind of ODE, we call it a stiff ODE. Okay, yes? Okay, so as I said, the step size is expected to be extremely small in some regions where the curve displays some variations. And then there are some areas where here you see that, for instance, the curve straightens out to a line with slope nearly 0, right? And I expect that because the curve is almost flat and not too much variation, I do not expect really in such region. I mean, in these regions, I kind of expect you have some huge slope and some huge variations, but in this region specifically, where there is not too much variation, apparently, I do not expect a large number of steps to be taken, but you see that it is. You see here, look, it's not. In this proper ODE 23S, it's just this region is just taken with like 7-8 steps. Well, here, I don't know, probably 4,000 or 5,000 or 6,000 steps out of 12 or maybe more. Okay, so that is the sign of stiff ODE. There is not a very clear thing. So just by looking at something, if you give me an ODE and say, hey, is this stiff or not, I cannot tell you right away. I need to apply some solvers like this ODE 45 or something and see whether they can handle it with a reasonable number of steps or a lot of it. And then from there, I can tell you whether it's stiff or not. Okay, so it's kind of a trial and error to detect it. Okay, so here I'm going to show you the MATLAB code. Again, this is the flame propagation ODE that I'm going to simulate. And this is going to really show itself when you use a small value for delta. I'm going to use also small relative error here to make it accurate. And this ODE does actually have an analytic solution, which is y equals 1 over w. This w is a function of a e to the a minus t plus 1, where a here is 1 over that delta minus 1. And this w is the solution to this equation, w times e to the w equals z. So it's kind of like y times e to the y equals x. It's a root finding implicit thing. And this w function is what we call the Lambert function. Okay, so it is called the Lambert function. And clearly you have to solve it numerically in order to find it. But if you do, for a specific value of, in this case, this a, you are able to what? Or a specific value of x in this case, then you are able to find some analytic solution. And I'm going to show you in MATLAB, we can do it with the desolve command. So let's take a look here. So this is my inline function. I'm using a relative tolerance of 1e negative 4. And then here I show you that if the delta parameter is not very small, the ODE is not really that stiff. So I solve it one time with a delta of 10 to the negative 2, and it's not going to be a ton of steps. But if I reduce the step time, and that makes the whole simulation time span large, now you start to see a lot of what? A lot of steps taken. And then I solve it again with the same delta, but I solve it with this ODE solver, ODE23S. This S is for stiff, and that's because this one is designed to handle stiff ODEs, and it is going to use far less number of basically step points, right, or samples, a smaller number of samples. So here we go. Look. This is with delta of 0.1, and this is with delta of 0.0001. And you can see that instead of 185 steps, now you're looking at 12,000 steps here. Okay? And you might say, well, the simulation time is bigger. True, but the behavior of the curve has not. It's still this kind of sigmoid curve, and there is no reason for this region to have all those samples because the behavior is the same. So ideally, even if I increase this simulation time, it should have handled it instead of 180 with something like, I don't know, 500, 400, something like that, not 12,000. That is too much increment, okay? And this is not really something super acceptable. And here, as I told you, if you zoom into this region, it looks like, yeah, it's flat, but it's not. Look, if you zoom in, you're gonna see all these ups and downs here, all these overshoot, undershoots, and all of these edge changes, okay? So it's not as nice as you think it is when you zoom in, and it's the same for here too. I mean, if you zoom into this area, it's similar but not as bad, because in this case the delta is not very small, so you see oscillations but not as bad. So this ODE is really stiff, as I said, when that parameter delta is small and the simulation time is large and the initial condition is very small. That's where it shows the stiffness. Okay, good. And now if you look at this one, you see the same delta, the same everything, 12,000 steps. But if you look at ODE 23, look, everything the same, only 100 steps. Only 100 steps. And if you put them side by side, you see the results are very similar. Look, They are showing the same thing, but here, this one is handling this region much better than the ODE45 does because this is designed for stiff ODs. Good. So I'm going to share this file with you so you can play with it. Another equation that is shown on MathWork website is the equation of the van der Pol oscillator. And if you want to know what van der Pol oscillator is, I recommend you watch that video I have for it under my dynamics playlist. Okay, that's right here, and there are lots of interesting properties about van der Pol oscillator, like it has a limit cycle, a stable limit cycle, and the equation for it, you can see it's a second order system with a nonlinear damper, and you can see that. And if you want to simulate the van der Pol oscillator and solve its second order ODE with ODE45, again, you're not going to have a very nice time with that because that is a relatively stiff ODE. You better solve it with something like ODE23S. Okay? So I guess I mentioned all of this for you. And one important thing now, one major difference between ODE45 and the explicit solvers that I mentioned in my previous video when I talked about variable step size solvers, these ODE45 and the other group of ODE solvers that come with it, they are not for stiff ODEs, as I mentioned, and they are all explicit solvers. The ones that are used in MATLAB for handling stiff ODEs, they are all implicit solvers, okay? And I just recently published a video on the difference between explicit and implicit. So the stiff solvers are all implicit. What are they? ODE15S, ODE23S, 23T, and 23TB. Okay? Now, of course, they do more work per step because they have to solve that stiff equation. But since they take far less number of steps, at the end of the day, they have improved efficiency and improved numerical stability. So in general, in MATLAB, if you want to know what kind of solver to use, you come here and you look at different variable step continuous solvers. You need to answer a couple of questions. First, does your model contain any physical modeling components? If it's not, then so basically it's a simple offline or not real-time ODE you want to solve. Now if it's not stiff, then as I said, you solve ODE with ODE45, 23, or 113. If it is stiff, then you use these stiff solvers, okay? And also you can use this stiff solvers if your model does contain physical modeling components. Okay, so a couple of other things about the stiff ODEs that I need to discuss. One of them is called stiffness ratio. What is that? If I give you a first order linear ODE with constant coefficient A and non-homogeneous y prime equal AY plus F, where this A is a diagonalizable matrix and it has this distinct eigenvalues lambda t, where t goes from 1 to the dimension of A, right? Now, you know that if all of the eigenvalues of A, they have negative real parts, whether they are either real negative or if they are complex, their real part is negative, then the system is stable, means the value of y of t does not go to infinity as t goes to infinity. It stays limited, most of the time converges to 0, and then especially if it has negative real parts. And then the total solution can be written as this homogeneous solution, right, which is a combination of some exponentials, where the power in that exponential is the eigenvalue of A, correct? So this is the y homogeneous, and then it has this particular solution, right, which does depend on this function f of x, right? Good. And the homogeneous solution does go to 0 if the real part of these lambdas are all negative. Fine? Now, here, if we sort these lambdas, these eigenvalues, to be between two numbers, lambda under bar and lambda over bar, okay? So if the real part of these lambdas, which we assume they are all negative, if the absolute value of them are between some lambda over bar and lambda under bar, then the ratio of the real part of lambda over bar to the lambda under bar, that is called the stiffness ratio. Well, what does that mean? So let's say, for instance, my A matrix has, for instance, 3 lambdas, okay? The first one is, or yeah, let's say it has 3 lambdas, or you know what, let's make it more. Let's say, because you know they show up in complex pairs, right? So let's say one of them is the couple of them, lambda 1 and 2, are, for instance, negative 3 plus minus 3 times j, and then lambda, let's say 3 and 4 are like negative 2 plus minus 5 times j, and then I have a lambda 5, which is like negative 1, correct? And let's say that's it. Okay, I got 5 lambdas. So if you look at the real parts of these lambdas, if you look at their absolute value, this is the one that is the smallest absolute value, and this is the one with the absolute value largest. So here, this guy is that negative 3, and this one is that negative 1. So the real parts of all lambdas, their absolute value is between 3 and 1. So if you plug that 3 and 1 here, you see the stiffness ratio for this system is equal to 3. And of course, the bigger this ratio is, it means that you have some very slow transient response compared to what? Some very fast transient response. Okay? And this basically big difference between the speed of these transient responses is what makes these ODEs stiff. Okay? Because the behavior of the system can vary in some regions. Okay, this guy goes to 0 fast, and it initially affects the behavior much, and as it moves forward, that term will decay to 0, and then this one will affect. So the behavior of the system does change as time goes on. Some of these exponentials very fast for small t's, they would go to 0. But some of them, they go a lot slower to 0, and they show themselves for a bigger range of t. Okay, so instead of all of them kind of converging at the same time, because if they're all the same, your response is mostly kind of like that. But if one of them is a fast one and one of them is a small one, now you're going to have something like this. You're going to have more oscillations. Okay? And clearly this one shows a more stiff behavior than the other one does. So this stiffness ratio could be a measure of how bad the system can show stiffness, the differential equation, if it's linear. Now, most of the times your ODEs are nonlinear, like this guy here. Here is a nonlinear ODE. And in this case, I don't have an A matrix, and I cannot find the lambdas for it to form this formula. Well, what you can do is to basically at specific locations of y and t, you can linearize this system and look at the equivalent linear version of the system and the A matrix of that and the lambdas of that, but that's just a local analysis, not a global one. So in general, analysis of nonlinear ODEs is harder. Finally, the two properties I want to mention is A stable and L stable for stiff problems. What are they? So it says behavior of numerical solvers of stiff problems on stiff ODEs can be analyzed by applying them to some test ODE y prime equals k times y, for which we know there is analytic solution, y equals e to the kt, or y0 times e to the kt, correct? assuming that this k is a negative part or it has a negative real part. So this k in general could be a complex number. Yes. And to make it simpler, we assume that y of 0 equals 1. So this initial condition here is simply 1. Okay. So we know the exact solution of this simple ODE for a specific k. Good. Now, if we solve this simple first order linear ODE for a given k, and the solution from the numerical solver, if that solution approaches to 0 as time goes to infinity, when the real part of the k is negative, okay, yes, which is the same behavior as the actual solution does, because the actual solution, when t goes to infinity, clearly y goes to 0. So if your numerical solution shows the same behavior for a fixed step size, not a variable one, for a fixed step size, if you use your solver but with a fixed step size, and as t goes to infinity, or in your case as the number of iteration goes to infinity, you see that this y of n goes to 0. That means your method, and remember this A stable is defined for the method, not for the ODE. The ODE is stiff. The numerical solver is then will be called A stable. Okay, so A stable numerical solver is the one, again for last time, when you apply it to the simple ODE, test ODE, when the number of iteration goes to infinity, the solution approaches 0, assuming that you're using a fixed step size. On the other hand, if the solution can approach 0 in a single step, not in a ton of steps, but when the step size goes to infinity and the solution goes to 0, still that is a stable solver, but we call it L stable. Okay, so you see the difference? A stable means what? Means h is some limited constant number, and it's not very big, okay? And the number of iteration gets large, your solution goes to 0. On the other hand, L stable means you only use one iteration, but this h can be very large. Still, y of n, or y of 1 in this case, goes to what? Goes to 0. Then we call it L stable. Right? And you might say, well, is that showing the same behavior? Yes, of course. Here, if this t goes to infinity, I can say that this t goes to infinity either in one step with a huge step, or in a ton of steps, but with what? With a smaller step size. The result for both of them doesn't matter. The result is y should go to 0. The second one is a stronger condition. The first one is a little bit weaker condition. So here, to demonstrate that for you, to clarify that for you, we're going to apply some solver to this test ODE, and we'll see if this method is A stable, L stable, or not. So the first one we're going to check is the Euler method, the simplest of all. We apply to this ODE. Remember, we assume that y of 0 is 1, and we assume that h is constant. We are checking the A stable first. The update equation for Euler is this: y of n plus 1 equals y of n plus h times the right-hand side. In this case, the right-hand side is what? Is k times y. So this function becomes k times yn, correct? And these two both share yn, so if you want, you can factor yn out, and it becomes 1 plus kh. So that is yn plus 1 in terms of yn, y plus hk. Now, if you expand this and go all the way to 0, you'll see that yn is going to be a geometric progression in terms of the previous y's, right? So it's going to be 1 plus hk to the n, or times y naught. Now the question is, would this solution go to 0 when this n is increasing to infinity? Would this yn go to 0? That is the solution. Okay, so will my yn go to 0 as n gets very big? Well, let's find out. Does it? Well, that depends on this term here. This is a term like 1 plus z, the whole thing to the n, right? Geometric progression. And this 1 plus z, where z is this hk, by the way, we show it by phi z and we call it the stability function. This function should go to 0 because y0 is clearly not equal to 0. So this term should go to 0. And this term, as I said, this is a geometric progression. It only goes to 0 when the magnitude of this term, which is raised to power n, is less than 1. Yes? Okay? So only for those z's for which the magnitude of 1 plus z is less than 1, this system, the solution of it, will go to 0. Now, in the z-plane, if you want to plot that, what kind of plot would that be? Well, this is the z-plane here, okay? Yes? And magnitude, where is z? 1 plus that, which moves your z from here to here. The magnitude of that, which is basically the distance of the points from this location here, -1 and 0, the distance of them is less than 1. So those points should fall inside the circle with a radius of 1 and centered at -1 and 0. Yes, this is your z-plane. So this is the real part of z, and this is what the imaginary part of z. So it is only stable, it is only going to 0 for the z's in this region. And remember, z was what? It was k times h. So you see, it is not going to converge to 0 for all potential z's, just for a portion of it. Right? We said that it is astable if, as long as the real of z is negative, it converges to 0. But remember that here, all of this region on the left side of the imaginary axis, they have real of z negative. So basically, only for the region inside the purple circle, it is converging to 0, and not for the rest of this hashed area. Therefore, this algorithm is not what? Astable. Okay, so this one is what? Is not astable. And clearly, if it's not astable, it's definitely not L-stable too, because L-stable is a stronger condition. Okay, now as another example, and before I move to the other example, just what kind of numbers would not work here? For instance, let's say the real of z is -15 somewhere here, which is clearly fitting my criteria. But if I pick my h to be 1/4, if you multiply h by k, clearly -15 times 1/4, this is going to be -3.75, which is clearly here outside the circle. You see? So it doesn't work. So if I want the real of k to be -15, I should pick a k for which the magnitude of this product is less than 1. So for instance, h should be what? 1/16. Then yes, it falls inside the circle. Okay, so it's not going to work for every h, just for specific h's given some specific case. Good? Now here, we look at another solver, the trapezoidal solver. The trapezoidal solver, if you apply to the same ODE, the update equation for that is yn plus 1 is yn plus half of the step size times what? The right hand side at the current time point and current y, and f at the next time point and the updated y. As you can see here, clearly this is an implicit solver, because y appears here and here. This is not directly yn as a function of yn plus 1 as a function of yn. So this guy is what? This is an implicit solver. While the previous one is clearly what? As you can see, this is an explicit solver. So what happens to this implicit solver? In this case, the f function is very easy, simply k times whatever is inside of it. So this f is going to be k times yn, this one is going to be k times yn plus 1, right? So your equation is yn plus 1 equals yn plus h over 2 times k times yn, and then plus h over 2 k times yn plus 1. And this is the case that this term is linear, so you can bring it here and find this analytic solution for it. So you see, this is an implicit explicit solver, right? So if you want, you can say implicit explicit in this case, and so this kind of acts like an IMEC solver. Okay, now if you look at this, in what region this guy is going to converge? Again, here we assume this hk is your variable z, so your stability function phi of z is going to be 1 plus 1/2 z over 1 minus 1/2 z. And if you want to know this guy, in which region it is going to go to 0, why should it go to 0? Because from here, your yn is clearly that term to the n times y0, and y0 is 1, so it is 1 plus z over 2 to 1 minus z over 2. Right, so this is the function for which the magnitude should be less than 1, so this geometric progression goes to 0. And for what region of z the magnitude of this is less than 1, if you know complex numbers, you can see that it is literally the entire negative side of the imaginary plane. So all of the region for which the real of z is negative will match this condition, and so this method is A-stable. What about the L-stable? Is this method L-stable? In that case, what we need to do is to make sure that this h is going to infinity, but this n is just 1. So we take one step, and we want to know whether the limit of this y1 as h goes to infinity is going to go to 0 or not. If it is, then it's L-stable as well. Now, what is y1 in this case? So this is going to be the limit of y1. If we write it, it is going to be 1 plus hk over 2 to 1 minus hk over 2 as h goes to infinity to the power 1 times 1. Right? Let me do that portion. And is this going to 0 for any k for which the real part of it is negative? The answer is when h is very large, okay, the one term is negligible compared to that, and so you get k over 2 divided by negative k over 2, so you get a negative 1, basically. And clearly this is not equal to 0. So this method is not L-stable. Okay, it is A-stable, but clearly not L-stable. Okay, so here in this video we talked about what is a stiff ODE and what kind of solver in MATLAB we use to, or in other software as long as they have similar solvers, what kind of solvers we use for them. What is a stiffness ratio, which is an indication of the stiffness of a linear ODE. And finally, what is A stability and what is L stability, and also what is the stability function for what? For a solver of a stiff problem. So hopefully this video was useful to you. You got some knowledge. So when you go to MATLAB or any other software and it says, do you want a stiff ODE solver, you have some idea of what it is talking about at least. Thank you so much. I will see you in the next video.